Science isn't a tidy recipe. We're busting the straight line myth and showing the real process. Across this video, you'll see how questions become testable hypotheses, how experiments, data, and models evolve through debate and revision, and why peer review and replication make science self-correcting. We'll follow a gripping case, the messy, world-changing discovery of penicillin, to reveal chance, creativity, and collaboration at work. By the end, you'll know how to spot strong evidence, what theory actually means, and why science can change its mind and become more reliable. Stay with me. The real story is far more surprising than the simplified diagram. Every great scientific journey begins somewhere. It starts not with a known fact, but with a question, a curiosity, a hunch. This initial spark often takes the form of a hypothesis. Hypothesis can sound technical, but it's actually simple and fundamental. A hypothesis is a proposed explanation for something you observed. It's an educated guess, but a special kind. The crucial feature, it must be testable. It must make a specific prediction you can check. For example, a gardener notices some plants thriving more than others. They wonder why. That curiosity could lead to a hypothesis. Plant X will grow taller and produce more fruit if it gets at least 8 hours of direct sunlight per day. That's a solid hypothesis, clear and measurable. You can design an experiment to test it. You can measure the sunlight, measure plant height, and count tomatoes. A good hypothesis dares the evidence to prove it wrong. Its power is falsifiability. Falsifiable means some possible outcome could show the hypothesis is incorrect. If plants do just as well with 4 hours as with 8, the hypothesis is false. That's not failure, it's progress. Knowing what's not true moves you forward. Claims that can't be tested, like invisible, undetectable spirits, are not scientific hypotheses. Scientists often keep multiple competing hypotheses in play. They don't pick one and try only to prove it right. They propose several explanations and design experiments to see which fits best. Perhaps the plants are affected by the type of soil, the amount of water, or a specific nutrient. A good scientist tests all plausible ideas, acting as an impartial judge of the evidence, not a lawyer for one idea. This open-mindedness prevents getting stuck on a wrong idea just because it came first. Once a testable hypothesis is in place, the next phase of the scientific method begins. This is where theory is put to the test, where ideas meet the unyielding scrutiny of reality, the experiment. An experiment is a carefully controlled procedure designed specifically to test a hypothesis. It's far more than just trying something out to see what happens. The key is control. A good experiment is about isolating variables to understand cause and effect. The variable the scientist intentionally changes is called the independent variable. The factor they measure to see the effect is the dependent variable. Everything else that could possibly influence the outcome must be held constant. These are the controlled variables. Only by doing this can we be confident that any changes we observe are actually due to the one thing we altered. For our gardener, this might mean setting up several identical pots with the same soil and the same type of tomato plant. Some pots, the experimental group, would be placed where they get 8 hours of sunlight. Here, sunlight is the independent variable. Others, the control group, might be placed where they only get 4 hours. This group provides a baseline for comparison. Every other condition, the amount of water, the type of fertilizer, the ambient temperature, would be kept the same for all plants. These are the controlled variables. During and after the experiment, scientists collect data. Data is the plural of datum, and it simply refers to the information gathered from observations and measurements. These are the raw, objective facts that will either support or challenge the hypothesis. This information is not an opinion or a belief. It is a record of what actually happened. For our gardener, the data, the dependent variables, would include daily or weekly measurements of each plant's height, the number of leaves, the date the first flower appears, and ultimately, the total weight of the tomatoes produced by each plant. Data can come in many forms: quantitative data like numbers in a spreadsheet, or qualitative data like photographs, satellite imagery, or detailed written notes. Crucially, one experiment is almost never enough. The world is a complicated place, and a single test can be misleading due to random chance or an unforeseen error. What if an undetected pest attacked only the plants in the sunny spot? That would skew the results, making it seem like sunlight was harmful. This is why scientists repeat their experiments, a process called replication. They might run the same test multiple times themselves, and ideally, other independent scientists will try to replicate the experiment in their own labs, following the original method. The more times an experiment is repeated with the same outcome, the more confidence we can have in the results. This repetition is a core principle for building a reliable body of knowledge. But what happens when the data collected are messy and confusing? They might not give a clear yes or no answer to the hypothesis. The plants in the sun might grow a little taller, but not as much as predicted. Or perhaps they produce more leaves, but fewer fruits. This is not a failure. In fact, it's often the opposite. It's a new puzzle, an unexpected clue that points toward a deeper, more complex truth. This is where a scientist's creativity and insight come into play. They must analyze the surprising data and ask new, more refined questions. Maybe sunlight primarily affects height, but fruit production is more dependent on water? Or perhaps there's an optimal amount of sun beyond which the plant gets stressed? This leads to a revised hypothesis and a new round of experiments, each one designed to untangle another piece of the puzzle. This iterative cycle of testing, analyzing, and refining is the true rhythm of scientific discovery. It's a patient, persistent, and often surprising journey toward understanding. As data from many experiments accumulate, scientists need a way to make sense of it all, you know. They look for patterns, connections, underlying principles. This is where models come into play. In science, a model is not something you see on a fashion runway. It is a simplified representation of a complex system that helps us understand and explain how it works. A model can be a physical object, a miniature solar system with planets orbiting a central sun. It can be a mathematical equation, Isaac Newton's laws of gravity, or a sophisticated computer simulation that predicts weather patterns. Models are essential tools for thinking. They take a vast amount of data and distill it into a coherent picture. For example, after countless observations of planets and stars, astronomers developed the heliocentric model. This model explained observed planetary motions far better than the old Earth-centered model. Models are not perfect copies of reality. They are approximations. They strip away unnecessary details to reveal fundamental mechanics. Their value: explain existing data and make predictions about future observations. If a model proves incredibly successful, explains a wide range of phenomena, and survives rigorous testing repeatedly, it may be elevated to a scientific theory. Everyday theory can mean a hunch, but in science, a theory is the opposite of a guess. A scientific theory is a well-substantiated, comprehensive explanation. Theories: evolution, general relativity, germ theory, cornerstones of modern science. Even the most successful theories aren't absolute final truths. They are the best explanations we have, based on available evidence. Science is open to new data that might challenge a theory. If compelling new evidence emerges that a theory can't explain, scientists will revise it or rarely replace it with one that explains old and new evidence. This ability to change with new information is science's greatest strength. It allows our understanding of the universe to deepen and become more accurate over time. No scientific discovery is made in a vacuum. Science is a deeply social and collaborative enterprise. A global community constantly checks and builds upon each other's work. Two key mechanisms uphold this community: peer review and replication. When scientists think they've made a big discovery, they don't just announce it. First, they write a detailed paper describing their question, their methods, the data they collected, and their interpretation. They submit the paper to a scientific journal. This is where peer review begins. The journal editor sends the paper to several anonymous expert reviewers. Reviewers act as critical gatekeepers. Their job is to scrutinize the paper from top to bottom. Did the authors use sound methods? Is their reasoning logical? Do the conclusions follow from the data? They look for potential flaws, biases, or alternative explanations. They may suggest additional experiments, request clarifications, or recommend rejection for serious problems. This filters out weak or flawed research before publication. Peer review is an essential first check, but it's not infallible. The ultimate test is replication. Replication. Independent teams repeating the experiment to see if they get the same result. No connection to original researchers. If a team in California claims a discovery, can a team in Germany or a team in Japan reproduce it? If yes, confidence grows immensely. Replicated results across places point to real features of nature, not flukes. Failed replications raise red flags. It doesn't prove the original was wrong, maybe an undocumented detail, but the claim becomes disputed. That spurs a flurry of new research as groups investigate the discrepancy. Public challenge and retesting are how science self-corrects. Mistakes are inevitable, but peer review plus replication find and fix them, strengthening our collective knowledge. Science is rarely a straight line from question to answer. It's a winding path, full of dead ends, happy accidents, and crucial collaborations that are often edited out of the final story. To see how all these messy, interconnected parts of science work in the real world, we need look no further than the famous and often oversimplified story of penicillin. The popular version of the tale often focuses on a single dramatic eureka moment, a flash of genius from a lone inventor. The story begins in 1928. Scottish bacteriologist Alexander Fleming returned to his London laboratory after a 2-week holiday. Before leaving, he had been cultivating Staphylococcus bacteria, and upon his return, he found one of his petri dishes had been contaminated with a common blue-green mold. It was the kind of contamination that would lead most researchers to simply discard the plate and start over. But Fleming noticed something strange. In the area immediately surrounding the mold, the colonies of bacteria had been destroyed. A clear, lifeless ring separated the fungus from the thriving bacteria elsewhere on the dish. This was a brilliant observation, the spark of a new idea. Fleming formed a hypothesis. The mold was producing a substance that was lethal to bacteria. He was right. He isolated the mold, identified it as being from the Penicillium genus, and managed to grow it in a liquid broth to test its properties. He found that this mold juice, which he named penicillin, could kill a wide variety of harmful bacteria, including those responsible for scarlet fever, pneumonia, and meningitis. This is often where the simple story ends, with Fleming as the sole hero of discovery. But this was not the discovery of a usable medicine. It was the discovery of a curious phenomenon. Fleming's initial attempts to purify the active substance were unsuccessful. The active ingredient was incredibly unstable, losing its potency quickly, and it was extremely difficult to produce in any significant quantity. He simply lacked the chemical expertise to isolate it. He published his findings in 1929, but for over a decade the discovery languished. A scientific curiosity largely ignored by the medical community, which was focused on the new sulfa drugs. The real breakthrough came more than 10 years later, driven by the desperate pressures of World War II. With soldiers dying from infected wounds, the need for new antibacterial agents was urgent. A team of scientists at Oxford University, led by pathologist Howard Florey and biochemist Ernst Chain, were systematically searching for natural antibacterial compounds and stumbled upon Fleming's old paper. Intrigued, they decided to take on the challenge that Fleming could not overcome: purifying penicillin and producing it in large enough quantities to be used as a drug. Their work was a monumental effort of trial and error, a masterclass in scientific problem solving. They experimented with different methods of growing the mold and extracting the active compound. It was slow, frustrating work, requiring ingenuity and persistence. They were not just following a recipe, they were inventing one, developing a new technique called freeze drying to stabilize the fragile compound. Finally, after many failures, they succeeded in producing a small amount of a stable, purified penicillin powder, a few precious specks of brownish dust. They tested it first on mice, and then, in 1941, on their first human patient, a policeman suffering from a severe infection. The results were miraculous. The man began to recover, but their supply was so limited that they had to recycle the penicillin from his urine. When they ran out, the infection returned, and he died. The tragic outcome proved the drug worked, but also highlighted the desperate need for more. With Britain under siege, Florey traveled to the United States to seek help. This led to a massive effort to find better, higher-yielding strains of the mold, famously including one found on a cantaloupe in a market, and to develop industrial-scale production methods using deep vat fermentation. By D-Day in 1944, enough penicillin was being produced to treat all wounded Allied soldiers, becoming the wonder drug that saved countless lives. The story of penicillin is not one of a single, straight-line discovery. It is a web connecting Fleming's accidental observation, the dedicated teamwork and chemical brilliance of Florey and Chain, the industrial might of a nation mobilized by war, and the contributions of countless unnamed technicians and scientists, all spanning more than 15 years. It is a perfect example of how science truly works, a blend of chance, curiosity, persistence, and collaboration. Given that science is messy, that it's profoundly human, often painstakingly slow, and filled with mistakes, dead ends, and course corrections, you might be tempted to ask, how can we possibly trust it? It is a fair and vital question. The process can seem chaotic from the outside, like watching a kitchen during a dinner rush. The answer lies not in the perfection of any single scientist, because no scientist is perfect. Nor does it lie in the infallibility of any single study, because every study has limitations. Instead, our trust is placed in the strength and integrity of the overall system. Science is not a belief system built on faith or the authority of a few. You are never asked to simply believe a scientist. It is a process, a structured method of inquiry built on foundational pillars. The first is skepticism, the practice of questioning claims and demanding proof. The second is transparency, sharing methods and data so others can examine the work for themselves. And the third is a relentless commitment to evidence, allowing the facts to lead the way, even if they contradict our favorite ideas. Its trustworthiness comes from the fact that it is designed, from the ground up, to be self-correcting. No single study is ever the final word. Think of it as the first sentence in a global conversation. A surprising new result is met not with blind acceptance, but with a wave of healthy, constructive skepticism from the scientific community. Other scientists will immediately ask questions. Was the experiment designed properly? Were the controls adequate? Could there be another explanation for the results? Was a potential bias overlooked? And most importantly, can the result be replicated? Can another lab, using the same methods, get the same result? This culture of critical evaluation and independent verification is what allows science to filter out errors and build a reliable body of knowledge over time. Individual findings may be tentative, like a single thread, but when dozens or hundreds of studies conducted by different teams all over the world all point toward the same conclusion, those threads are woven together into a strong rope of scientific consensus. Our confidence in that conclusion grows immensely. This is why science can change its mind without it being a sign of weakness or untrustworthiness. In fact, its ability to change in the face of new, stronger evidence is its greatest strength. When new tools like the James Webb Space Telescope or advanced DNA sequencing allow us to see the universe in a new light. They sometimes force us to update, refine, or even replace our old models. Newton's laws of gravity were not wrong. They were an excellent approximation that works perfectly for launching satellites and building bridges. But Einstein's theory of general relativity provided a deeper, more accurate picture that also explained the orbit of Mercury and the existence of black holes, phenomena Newton's laws could not. This is not failure, this is progress. It's the system working exactly as it should. So how can you engage with this process in your own life? Be curious, ask questions, but also be critical. Adopt a bit of that healthy scientific skepticism. When you hear about a new scientific claim, especially one that sounds dramatic, pause and ask those key questions. Was this a single study, or does it represent a broader consensus? A single study is a starting point, not a conclusion. Look for what the wider body of evidence says. Who funded the research? Is there a potential conflict of interest that might influence the results? And have other independent teams confirm the findings? Replication is the gold standard of reliability. Science matters profoundly. It has doubled our lifespan through medicine and public health. It has fed billions by revolutionizing agriculture. It has allowed us to walk on the moon and peer back to the dawn of time. We can trust it not because it is perfect or all-knowing, but because it is a process of continuous improvement. It is a collective, global, human effort to honestly and humbly question the universe, and to listen carefully, patiently, and openly to the answers it provides.